Okay, ladies and gentlemen, welcome to section 1.5, dealing with graphical transformation. We're going to look at some things called rigid and non-rigid transformations. You might remember if you got to a certain question on one of your iReady questions, they may have talked about a thing called rigid motion. Might not have remembered what that meant, but I'm going to explain it to you in a few moments. All right, so moving forward into translations, or part of our transformations. Translations, basically in our idea, is going to mean moving left or right, up or down. So first of all, let's look at what a vertical translation is going to do, or going to look like. A vertical translation would be taking a function like a square root of x and adding something on the outside of that function. Let me get my pen up here. If, like I said, if our function was the square root of x, and I was to add something on the outside, here we go, square root of x, if that's our function, if I wanted to move up 3 units, I would be this. And that would take our normal square root function that does this, which we've looked at the parent functions, and it would move it up. It would move every point up 3 units. So I call this outside the function because that plus 3 is outside the parent function of the square root of x. And this version is whatever you think it is. If it's a plus, it goes up. If it's a minus, it goes down. It's moving the y values up 3 units or down 3 units, depending on the sign. Horizontal translations, well, if vertical is on the outside, horizontal is going to be on the inside, and that would be adding or subtracting something to the inside of a function. So if, like I was saying, if we said our function was the square root of x, and I wanted to move it 3 units up, I would add 3 to the outside. However, if I wanted to move it 3 units to the left, let's call it new h of x. If I wanted to move it to the left, you have to actually do the opposite of what you think. In order to move left, you think minus. But it's left if it's a plus. It's basically thinking about what makes it 0. So if I wanted to move it left 3 units, I would say x plus 3 under my radical. So the square root of x being our parent function. If this was our parent function, square root of x, the square root of x plus 3 is going to be 3 units to the left, and it's going to look identical, or close enough to identical. Now, okay, left if positive, right if negative. This, moving up or down or left or right, these are rigid transformation. Rigid transformation just means I'm just sliding it around. I'm moving the same exact function to different spots on the graph. And our non-rigid, well, sorry, this is still been rigid, but it's not going to be a non-rigid. Okay, I forgot I did reflections first. All right, so reflections are also going to be rigid motions, or at least I think they're rigid motions. If we wanted to reflect a function across the x-axis, or about the x-axis is usually how things are worded, we would take the opposite of the original function. So that would make all of my y values negative, or all of my negative y values positive. So we put a negative on the outside of the entire function. So if I said our g of x is the square root of x, the square root of x looks like this. And if I said, okay, now my reflection across the x-axis is the opposite of the square root of x, that's just going to flip me over upside down. It's going to flip all of my y values to the other side of the x-axis. So what this does is it makes all of my xy values x and the opposite of y. So it changes the sign of all of my y values on my function. Okay, so if you kind of think about it, if I wanted to change it across the x-axis, I have to change all my y's. So in order to go across the x-axis, I need to change all of my, across the y-axis, I need to change all of my x's. So in this case, we're going to take f of negative x. So we're going to change it to the inside of the function. Call it h of x is equal to the square root of negative x, or the opposite of x. Now, some of you might be a little bit worried here, saying that that's a negative under my radical, but that's not true. This says take the opposite of all of my x's and square root them. So if I have positives, I now want the negative x's. And if this is my parent function up at the top, the reflection across the y-axis is going to be that. So I've changed all of my x values to opposite of x values. So notice I use the words outside and inside quite often in this. If I change stuff on the outside, it affects the y values. And if I do stuff to the inside, it affects the x values. So make sure you understand what that means. Now, stretches, like vertical and horizontal stretching or shrinking or compression, whatever you want to call them, these are non-rigid because these change the overall shape of the function. If we were to do vertical, well, vertical is the y values, so we need to multiply on the outside of the function. So again, we're going to multiply some value to the outside of the function. And if c is bigger than 1, it stretches it by a factor of c, so it makes it bigger. So if we were to do, again, square root of x, looks like this. At x equals 9, y equals 3. But if we were to take a stretch, a vertical stretch by a factor of, let's say, let's say 2, that vertical stretch is going to do this, and then when it comes up here, at x equals 9, it's no longer 3, but it's twice that height. It's at 6. So I've changed the height of all of my y values. If you notice here that it's a stretch, if c is bigger than 1, it's a shrink if c is some fraction. So if c is between 0 and 1, if I wanted to do the, let's call this h of x, if I wanted to do it 1/2 of the square root of x, it doesn't stretch, it doesn't get bigger, it gets smaller. So instead of at x equals 9, it should be 3, it actually comes out to 1.5. It changes the height of my function right there. So it shrinks it down. Some previous teachers have called it compression, and it compresses the function down by half. Okay, so likewise, if we can stretch the x values, we can also stretch the we've stretched the y values, now we can stretch the x values. So that would be a horizontal, because horizontal changes the x values. This would be multiplying by the inside of your function. Now, it's opposite. Every time we do something to the inside of a function, it's kind of opposite what you think. If that number is between 0 and 1, it actually stretches by a factor of 1 over c. Let me erase my pen here. Just a second. So we're going to keep with the square root of x going here. So if I said 1/2 x, this means it stretches by a factor of the reciprocal of 1/2. So this stretches by 2, so it doubles my x values. So normally, when y is 3, x is 9. However, now when y is 3, x has to be 18. So it stretches me left and right. It stretches the width of my function. And likewise, if c is bigger than 1, it's going to shrink by a factor of 1 over c. So I'll explain that momentarily here. If we were to do the normal function, I'm going to change my numbers here, but if I did the normal function and I said, let's go j of x, and we're going to call it the square root of 2x, 2 is bigger than 1, so therefore it's actually a shrink by 1/2 because it's cutting all of my x values in half. So normally, again, I should be at 9, 3. But this particular graph says when y is 3, x should be 4.5, half of it, half of the original x value. And that kind of makes sense if you think about it, because if I plug in 4.5, 4.5 times 2 is 9, and the square root of 9 is 3. So you notice this shrinks my x direction by half. Okay, so now to explain my double star there. The textbook teaches this in a slightly different way. Please do my version because it makes a little more sense. Be careful when you try to read the book because their way is not going to make sense compared to my way. Here's your assignment, but I'm going to leave you with this example. If I said I had the function like this, we should be able to look at this function and know what's going on. We should know that it's a quadratic. Oops, that's not how you spell quadratic. It's a quadratic. Its parent function is x squared, because this is an x squared. We should know from today's lesson, or we should learn from today's lesson, that the minus 3 says take this parent function, go down 3 units. And if we think about just taking the vertex, by the way, we could take that vertex down 3 units. This minus 1 tells me go right 1 unit. And this positive 2 says a vertical stretch by a factor of 2. So the first two, the down 3 and the right 1, say move all of your x values down 3 and right 1. And the vertical stretch says now double the height of all of your y values. Okay, this becomes very important for us because every single function we do can be talked about as a transformation, especially when we get, as a hint here, to something like this. This talks about transformations. We don't know how to graph this yet, but we will in the next couple months. All right, I'm going to leave you guys with that, and I will see you guys tomorrow.